Our goal when writing down a random utility model is to identify and estimate the parameters from our specification for the representative utilities v and j. In the car versus bus example from the previous video, we supposed that v and j is equal to beta multiplied by t and j plus gamma multiplied by m and j, where t and m were the time and monetary costs of a given mode of transportation, j, for a particular decision maker, n. Here, the parameters of interest are beta and gamma. We say that a parameter is identified if it could be uniquely determined by observing the whole population of data from which our sample was drawn. Fundamentally, then, identification is about what we can and cannot observe from data. In the context of random utility models, the relevant question is, given that we cannot observe utilities, what can we learn from choices and attributes? There are two crucial insights for answering this question, both of which I hope are familiar from your coursework in microeconomics. First, only differences in utility matter. And second, the scale of utility is irrelevant. We'll explore each of these consequences in turn. We assumed that our decision maker Alice chooses the alternative with the highest utility, namely the I, such that UNI is greater than UNJ for all j not equal to I. Subtracting u and j from both sides of the inequality, this is the same thing as choosing the alternative I, such that UNI minus UNJ is greater than 0 for all j not equal to I. In other words, all that matters is how much better or worse a given alternative is than the others. Stated in terms of choice probabilities, the probability that UNI is greater than UNJ for all j not equal to I is equal to the probability that UNI minus UNJ is greater than 0 for all j not equal to I. We'll explore three consequences of this fact. First, only differences in errors matter, not the errors themselves. Second, we cannot identify a different intercept for each alternative. And third, we can only identify differences of effects for decision maker attributes. From the perspective of choice probabilities, all that matters is the difference between error terms, not the error terms themselves. Define epsilon tilde njk to be the difference epsilon nj minus epsilon nk. Taking this idea further, define bold epsilon tilde ni to be the vector of all unique differences that take epsilon ni as the base case. For example, consider a setting with 3 alternatives and thus 3 error terms, epsilon n1, epsilon n2, and epsilon n3. Here, we could calculate 2 differences relative to the first error term, namely, epsilon tilde n1 is equal to epsilon n2 minus epsilon n1 as the first element, and epsilon n3 minus epsilon n1 as the second element. If there are j alternatives, then there are j errors, and consequently j minus 1 unique differences. Defining G to be the joint density of epsilon tilde ni, we can calculate choice probabilities as follows. Pni, which we defined to be the probability that UNI is greater than UNJ for any j not equal to I, we know is equal to the probability that epsilon nj minus epsilon ni is less than Vni minus Vnj for any j not equal to I. Using our new notation, notice that that difference of errors on the left-hand side is epsilon tilde nji. So the choice probability is equivalent to the probability that epsilon nji is less than vni minus vnj for any j not equal to I. And this probability can be calculated from the following integral, where we integrate against the density of these error differences. Epsilon ni is the vector of all, I should say epsilon tilde ni, is the vector of all of the epsilon tilde njis. In other words, all the differences between each of the error terms and the error term epsilon ni, which is to say j minus 1 unique differences. So what does all of this have to do with identification? Let's revisit our car versus bus example from the previous video, but now we'll add in an intercept, alpha car for the representative utility of taking a car, and alpha bus for the representative utility of taking a bus. So what has changed by adding in these intercepts? As you may recall from your lectures on linear regression, adding an intercept to a model is a way of absorbing a non-zero mean from the error term. So suppose, for example, that the true utility, unj, is equal to x prime nj beta plus epsilon nj star, where x nj excludes a constant. So the first element is not 1. Then, if we define alpha j to be the expectation of epsilon star nj, and then we define epsilon nj with no star on it to be the difference epsilon nj star minus alpha j, then by construction, we have an equivalent model of the form unj is equal to alpha j plus x prime nj beta plus epsilon nj, where this new error term, epsilon nj without a star on it, is equal to 0. So compared to our original car versus bus example from before, this new version has the mean of the error for car and for bus both equal to 0. Now, when deciding whether to travel by bus or by car, Alice only needs to consider the difference of utilities. So, subtracting these two equations, we find that u bus minus u car is equal to alpha bus minus alpha car plus beta multiplied by the difference t bus minus t car plus gamma multiplied by the difference m bus minus m car plus the difference epsilon bus minus epsilon car. Notice that the two intercepts, alpha bus and alpha car, only enter this expression as a difference. This means that as far as Alice's decision is concerned, the only thing that matters is the value of alpha bus minus alpha car, not the values of alpha bus and alpha car separately. To make this more concrete, Alice doesn't care whether alpha bus is equal to 3 and alpha car is equal to 2, or whether alpha bus is equal to 101 and alpha car is equal to 100, because in either of these cases, the difference between the two alphas is 1. Because the specific values of each intercept can never affect Alice's choices, and because we only observe choices, not utilities, there is no way that we can tell alpha bus and alpha car apart. In other words, there's no way that we can separately identify them. We can only learn the difference of these two intercepts because it's the difference that affects Alice's choices. More generally, in a model with j alternatives, we can only identify the j-1 unique differences of intercepts. Another way of thinking about this is by designating one of the alternatives as the base case or the default, as we did when constructing differences of errors on the previous slide. We can only learn the differences of intercepts relative to this base case. Our car versus bus example thus far contains only attributes that vary depending on whether Alice travels by bus or car, the time and money costs of these two alternatives for Alice. In the language of our earlier video, these are attributes x and j of the alternatives. So what happens if we include an attribute Sn of the decision maker? In other words, an observed characteristic that doesn't vary with mode of transportation. Annual income is a good example, because this varies across decision makers. Alice may earn more money than Bob, but it does not vary across alternatives for the same decision maker. Alice's income doesn't depend on which mode of transport she chooses. Defining y to be income, suppose that the utility of traveling by car is equal to theta car times y, plus the time and money costs, plus the error, and similarly for u bus. Are theta car and theta bus both identified? In other words, can we identify the effects of income, y, separately for each of these two modes of transport, bus and car? Again, only differences in utility matter. Subtracting the difference in utilities, bus minus car, is equal to the quantity theta bus minus theta car times income y, plus beta times the difference of time costs, bus minus car, plus gamma times the difference of money costs, bus minus car, plus the difference of errors, bus minus car again. As in the example on the previous slide with the two different intercepts alpha for each mode of transportation, the income effects, theta car and theta bus, only matter for Alice's choices through the difference, theta bus minus theta car. And for the same reason, only this difference is identified, not the individual parameters themselves. In general, we can only identify differences of effects for decision maker attributes. We can't identify the effect of income on the utility of taking the bus, but we can identify how much larger this effect is than the effect of income on the utility of driving. Under our assumption of rational choice, Alice chooses alternative I if and only if UNI is greater than UNJ for all alternatives j not equal to I. For any constant lambda strictly greater than 0, however, this is equivalent to saying that lambda UNI is greater than lambda UNJ for all alternatives j not equal to I. This shows that rescaling the utility of each alternative by a positive constant has no effect on Alice's choices. To put it another way, the scale of utility is irrelevant. This seemingly trivial observation turns out to have quite important consequences for the identification of random utility models. Suppose we specify a model of the form UNJ equals xnj prime multiplied by beta plus epsilon nj, where the variance of the error term epsilon nj is sigma squared. Because the scale of utility is irrelevant, we're free to multiply both sides of the model by any strictly positive constant. If we choose to multiply by 1 over sigma, we'll obtain a rescaled model of the form UNJ star is equal to xnj prime multiplied by a new parameter vector, beta divided by sigma, plus a new error term, epsilon star nj, where the relationship between the two utilities is UNJ star equals unj over sigma, and epsilon nj star is equal to epsilon nj over sigma, so that the variance of this new error term, epsilon nj star, is equal to 1. Because the scale of utility has no effect on Alice's choices, there's no way for us to tell these two models apart given the data that we observe. This means that we cannot identify the scale of the parameter vector beta separately from the variance of the error term. Another way of saying this is that the error variance determines the scale of the coefficient vector. As we will show in our next video, any of the index models from our previous lecture can be viewed as a random utility model. And from this perspective, the rescaling that we required to be able to, say, compare logit and probit coefficients can be viewed as an example of this general phenomenon that the error variance determines the scale of the model coefficients. This arises because the standard logistic and standard normal distributions have different variances. The latter has a variance of 1, and the former does not.